sections, and the first one up is introduction. So let's start off with the question, what is Southeast Asian ophilocytosis? Southeast Asian ophilocytosis, or for short SAO, is an erythrocyte disorder where the erythrocyte change shapes, those morphology change to oval. And it's also genetically denoted in the deletion of 27 base pairs in the band 3 gene. One unique property of SAO that it is one of body's natural protection against malaria because of the changes of the structure, it becomes more resistant to the malarial infection. So there are two ways to diagnose SAO. First is by manual microscopy, and the second one is by using the PCR to detect the changes in the gene. But there are some problems. There is high prevalence of ophilocytosis in malaria endemic region, but there are a limited number of experts, and the manual examination is time-consuming. Therefore, we developed this automated detection to observe the changes in the morphology. To do so, we need the data. The data was obtained from Eijkman Institute for Molecular Biology, and it is originally malaria teaching slides for medical practitioners. There are two types of smear in the data set, thin and thick blood smear. So in the thick blood smear, we can see that the erythrocyte is already ruptured, so we cannot see the erythrocyte anymore. So because we want to observe the changes in morphology of the erythrocyte, that's why we use the thin blood smear. All images in the dataset was captured by using 5 megapixel Nikon digital sight DS5MC camera with 10 times 100 microscope magnification. And this is our proposed algorithm, and I'll go through it one by one by explaining the results. So we start by the image preprocessing. We take the original image and we convert it to grayscale by using luminosity. Using the intensity obtained from the grayscale image, then we create the binary image to separate the objects and the background. But as you can see, due to the biconcave structure of the erythrocyte, there are some holes present in the erythrocyte. And to counter these holes, we use the hole filling algorithm to fill these holes, and then an opening algorithm to smoothen the contour. Then this image is ready for segmentation. The goal that we are going to observe is the single erythrocytes, so we can extract its features. But you can see right here, there are some erythrocytes that are clumped to each other. So we need an algorithm to split these clumps. That's why we use the clump splitting algorithm. One of the clump splitting algorithms is bottleneck detection, which was introduced by Wang in 2011. In his method, he compares the Euclidean distance and the circumference of the clump. So bottleneck is defined as the smallest part of the clump. And the pair of points which produce the smallest cost function will be taken as the splitting points, and here is the result. So, but this algorithm is limited to clumps with two objects. How do we do this splitting for objects more than two? That's why we developed the novel algorithm called recursive bottleneck detection algorithm. So here we take the original image and we label and we note every area of the objects. The objects which area is bigger than the predefined area will be subjected to the clump splitting. So the input of the recursive bottleneck detection algorithm is the clump, the split, and is the segmented clump right here. So because this is still bigger than the predefined area, this will be split by using the bottleneck detection, and then this result will be checked. Is it still bigger than the predefined area? If yes, it will undergo the algorithm again and again until all the result is smaller than the predefined area. So after completing the clump splitting, now we have all single erythrocytes, and this can be the ratio by dividing major by minor axis. Then by using this ratio, we can separate the normal and oval erythrocyte. So in this research, we used the benchmark of 1.4. So every erythrocyte with ratio bigger than 1.4 will be calculated as normal, and erythrocyte with ratio of 1.4 or smaller will be calculated as normal. Then a count will be kept between these two categories, and then if the ophalocytes or oval erythrocytes exceeds 90% of the total erythrocytes, the image will be calculated as SAO positive. So now we have seen the whole algorithm. Let's take a look at the running time proportions. So the whole algorithm is divided to 6 steps, and we can see that the step that takes the most part is the clump splitting right here. This is due to how many numbers of clump that is being split in one image. So up to now we have discussed two important points that has been developed. First is the recursive bottleneck detection algorithm, which is a novel algorithm to split clumps with more than 2 objects. And the second one is an algorithm to split, to categorize which erythrocytes are normal and oval. So, but when we try to look, we have seen these 3 errors are present. And the first one is the preprocessing. So the preprocessing error actually lies in the hole filling. So the hole filling algorithm misidentified the background as a hole to be filled. So instead, it happens when the erythrocytes are forming this so-called border. So it fills the background and leads to clump splitting error. The second type of error is this erythrocyte extraction. So it happens because of the border and because of the bottleneck detection misidentified the splitting points, because these points produce the smaller cost function than the desired light lines. And then the last one is error in the feature extraction. So when we take a look at the classification, all images are classified correctly. But when you take a deeper look, the ratio produced was way bigger, and and after a closer look, it turns out that the minor axis obtained was incorrect. So because the major axis lies so closely to the image, the erythrocyte border, the erythrocyte border is taken as the minor axis instead of the desired minor axis. Okay, so as a summary, this is the summary of our whole algorithm. Starts from image preprocessing,